I want to welcome everyone here to our second session of the knowledge exchange among ACEC members in response to the 2025 Myanmar earthquake. And many of you have joined earlier in session one about a month ago. This is the second one, and there'll be a few more, at least one more, maybe two more after this. So, Sarosh, can you mute yourself, please? Sarosh, I can hear you. Okay. So, while we all went through the devastation, we could see the devastation in the March earthquake. I was looking at the news just about a few hours ago, and there was a huge, massive 8.8 magnitude earthquake that struck on the east coast of Russia, and and I'm sure it's a huge one. I haven't seen all the reports yet, but it's in our thoughts. Russia, the Russian Society of Civil Engineers, is a member society of ASEC, and then there are several in the Pacific, and there's warnings of tsunami going on, possibly even as we speak, um, all the way to the northern part of USA. So I hope everything goes right. Uh, but this is in the back of our minds while we do this. So anyway, uh, I want to welcome everyone here. Will the president of FedMES like to say a few words?
Thank you very much, Mr. Udai. On behalf of FMES, thank you for your cooperation and coordination for today's knowledge sharing, knowledge exchange program. Thank you. We just arrived from Nibiru, just like 12 o'clock. We have done the post-earthquake technical forum, 28 to 29, 2 days for forum, successfully completed and successfully finished. And I explained how to cooperate with your ACECC and FedMES for the knowledge sharing and technology for the earthquake engineering topics to the senior general, Mr. May Online, and higher authorities. They all also thank you to you, ACECC. Thank you very much. Thank you.
Thank you, President Pate. I want to point out that in the seminar that was held in the capital of Myanmar the last couple of days, we had an ASEC speaker from the Nepal Engineering Association take part as a key part of the speaker panel there. So thank you to NEA, and thank you to Engineer Bipin, who will also be a speaker here in this session. Okay, so we go with this session two. The first we have four speakers. One, the first one is from Institution of Engineers, Pakistan. Second one is from the American Society of Civil Engineers. Third speaker is from the Engineers Australia. And the fourth one is from Nepal Engineering Association. So the first speaker is Professor Rashid Ahmed Khan. Professor Rashid is a professor at NED University of Engineering and Technology in Karachi, Pakistan. And he has over 20 years of experience in leading and conducting research and development projects on design, seismic vulnerability assessments, and repair of civil infrastructure, including steel and RCC, for governmental and foreign consultants. He's published extensively in the form of research, book chapters, scientific articles, and he's dedicated to advancing the science and technology in bridge engineering, earthquake structural engineering, and climate change impact concerning flood resilience of civil infrastructure. His topic is seismic vulnerability assessment of RC bridges. So, Professor Rashid Khan, over to you.
Good afternoon, everyone. I hope everyone can hear me.
Yes.
Okay. So can I share my screen with you?
Yes, please.
So as Dr. Udai just mentioned that my topic is seismic vulnerability assessment of RC bridges. And this would be the presentation outline that first of all, I would discuss with you what difference exists between bridge condition assessment or vulnerability assessment. So both are more or less the same, but there is a difference in terms of assessments. Then I'll give you an overview of the bridge seismic risk assessment, how it has progressed and what kind of techniques that are available for assessment. And then I'll show you some of the vulnerabilities that we have seen in bridges in the previous earthquakes. And then these I will take into account, and then I'll discuss my seismic vulnerability of Pakistan, and then I'll discuss with you the 2005 earthquake, and you'll see how similar vulnerabilities existed in our structures. And already knowing these types of vulnerabilities, we still did not retrofit our structures. And then I'll show you another case study that we did for Karachi. We basically assessed all the bridges in Karachi for seismic vulnerabilities. So this is the presentation outline. So as you know, condition assessment is basically done for current condition of the bridge. And generally, when we talk of this condition assessment, it's for strength and integrity of the bridge for any defects or any damage that may have occurred during its service, so that the repairs or the re-strengthening can be done. And for that, generally, we have three basic techniques. The most easiest or the most common one is the visual inspection. If for any reason the visual inspection is unable to give us a good picture, then we can do non-destructive testing techniques can be applied on the system. Or if any further, that is for any member of the bridge that may needs to be further investigated, then we can do numerical or structural capacity analysis just to find out what the strength of the elements are, and accordingly we can then speculate what should be the repairs or re-strengthening them. Now, if you look at the structure vulnerability, this is an advancement to the condition assessment. It not only identifies the weakness, but the expected damage that may occur during a future event. And for that, the system has to be retrofitted. Now, for this, we have two basic techniques that are mostly used in vulnerability assessment. One is the risk assessment. Now I've added the word seismic because we are more interested in the seismic, but the risk assessment can be done for any type of structure. And the other part is the earth loss estimations. Now, the loss estimate is basically a quantitative term that we tend to use, and it's basically gives us the damage that may occur in terms of cost, or the repair of the cost, or the re-strengthening of, retrofitting of the, or what could be the delays if the system is unusable after the event. So that is one step further compared to the risk assessment. Now, the techniques that we employ for the vulnerability assessment are qualitative. Before that, we have a judgment approach, which was used up till 80s. Even the ATC 13 was developed using that. It's basically questionnaire based uh, qualitative technique where experts are using their knowledge, their experience. They basically define the damages that they see, and using that questionnaire they are able to develop statistical data, and that is then converted into models that can be used for the vulnerability assessment. The other one is the empirical. This is taken into account using the existing data of damages that are recorded in the past earthquakes of bridges, such as the Loma Prieta 1989 and the Northridge earthquake, uh, which was used to develop the FHWA manual. But again, this is very limited because in terms of the damage data may not be available for a single type of a bridge. So it's still has some uh, problems regarding the collection of the data. The third one is the analytical, which is the most commonly used because of the data unavailability. We can use models, numerical models of such facilities, and using that data, we can find out the vulnerabilities in the system. Here you can see I've given you a flow chart. Is for that the numerical is more likely to be used as compared to, and using the previous or the empirical data, we can combine them and develop a hybrid model, which is nowadays used mostly in these seismic assessments worldwide. And they are basically given as a function of fragility curves. And in order to develop the fragility curves, this is the equation that governs, and it gives us the probabilistic failure of an element or even a system with respect to the peak ground accelerations or velocities or even displacement. So nowadays, people, the government bodies or the worldwide, such as ASHTO, FEMA, they are basically using fragility assessments for their bridges or for their other structures as well. And for any of these systems, as I've shown you, not only we can find out the bridge damage, but we can further extend that and collect the loss estimations in terms of repair or even the bridge damage functionality relationship. So this can be further utilized for governmental bodies so that any budgetary or any schemes that they need to do, they are able to do it in within time before the event happens. Now, these are the failures that we have seen in the past earthquakes, such as unseating of the entire spans and or the which is the superstructure of the bridge. The others are at the bottom or the substructure of the system, where the other vulnerable parts are columns or piers, as we call them, and their foundations. So generally, most of the failures that have occurred are either these common ones that I've shown here, that where the uh, column rebarring, or it's usually not provided, or the detailing it's missing in these elements. So generally, either you have the shear failure, the confinement failure, or the crushing failure. So these are basically failures that we have seen in the previous earthquakes, and we have learned these lessons from them, that if there is uh, for example, if I take the approach slab, which is the entry or the exit point of the bridge, and it's generally placed on an ground itself. So basically, there could be settlement of the ground because of the shaking of the ground, or the expansion joints or the joints between the abutment as well as from the deck of the bridge. This could be misaligned because of this settlement, or it could overturn. So these are, like I said, the most probable failures. Causing forces would be the longitudinal forces, slope failure, lateral spread, or even liquefaction. So basically, from the previous studies, we know what kind of mechanisms exist for all the elements. And for each of these elements, the codes, the ones that we use for our seismic designs, have been updated. And each of these are basically provided with either the enough strength or the um I'm sorry, I'm just forgot the word. Detailing that should be kept for these seismic zone structures. So these are the common failures that we occur or we see, and generally, uh, if you take all of these in the superstructure or at the supports, at the piers, cap beams are basically pile beams, but you could have transoms as well, and then the abutments. All these failures were seen in the 2005 earthquake and subsequent earthquakes that happened in Arvaran in 2013, and then we have one in the again in the Kashmir region. So I'll show you again the damages that occurred, and but before I do that, I'm just going to show you what existed, what type of structures and what kind of knowledge existed before the 2005 earthquake. So most of the bridges that you'll see in Pakistan are slab girder bridges, with few exceptionally steel truss bridges. Here, the bridges are constructed on the basis of economics, not by the vehicular loading or the site location. So mostly because the slab girder bridges, which are RCC bridges in nature, they are cheaper to build, and generally you'll see them as simply supported up to 30 meters span bridges, or maybe up to 35 meters span bridges. And as I mentioned, because of the economics is governed, you'll see that throughout Pakistan, the variation in bridge is not that much. But as you go towards further towards the northern areas, which is now KPK, used to be called as NWFP, you had steel bridges that were constructed by the colonial or the Britishers when they ruled in Pakistan. So most, even nowadays, their structures are still being used, which have crossed their lifespans. And unfortunately, there is no monitoring of these bridges, but they are still in use. Now, the basic definition that was given in our design code, that was, remember, written in 1967. And it is a cut and paste of the British code. And the earthquake clause is basically cut and piece from the ASHO which was now known as ESTO, the American code of 1970. And they use this simple elastic equation where earthquake forces or the lateral forces that can be applied either to longitudinally, that is along the length of the bridge, or transversely, that is perpendicular to the longitude or the longitudinal of the bridge. It's nothing but C into D, where C is the percentage depending upon what kind of substructure you have. So for example, if you had footings, it will be 2% of the total dead load. If it's not, or the soil is much better, it could be up to 4. Or if the soil is very bad and the system is on resting on piles, which is generally the case, it could be 6% of the total dead load. But here you can see the equation is simple, and the design would become very simple in the reinforced concrete, but it deficient of the level of shaking or the seismic zoning of the level of that particular soil. Geometry of the structure, it's not taken into account. Similarly, no dynamic or non-linear dynamic method provision is shown, which nowadays is used in most of the design codes worldwide. Similarly, no detailing is provided for the ductility demands or the for the critical components as nowadays are used for RCC structures. Similarly, when you use the nonlinear, there are various parameters that needs to be investigated, plastic hinge locations, and so on and so forth. So nothing existed in our code. And I may remind you that this code is still being used and still is the current code of our design of our bridges in Pakistan. So it is still being used. And so you can see, we know what kind of deficiencies it has, but still most of our bridges are designed using this in conjunction with ASHTO as well. But if you design using this, it will be approved and it will be built. However, nowadays, like I said, we have started to replace this with ASHTO as well, but still, this is the only code that is available for Pakistan. Now, if I'll show you the earthquake that happened in 2005 and its devastation that it's caused, not only to the human lives, as you may already know, but it caused a lot of devastation in terms of lifelines on utilities as well as the infrastructure that was in place. So I'll focus myself on the bridges only at that time. So as you can see, there was a total of around 6,500 kilometers roads were damaged throughout the northern areas where the earthquake happened. And if you look at in terms of bridges, these were the bridges that failed. Sorry, the type of existing bridges that there were. We had RCC bridges, which were newly built, I would say. Then of the colonial rule, which were many, such as arch bridges, stone bridges, steel bridges. They were built by the Britishers or over a period of time. They were repaired and they were still in being used. So, uh, as we had already seen, these bridges have lot of vulnerabilities in their systems, and but like I said, our bridge design code does not take these vulnerabilities into account. So obviously, when the 2005 earthquake happened, most of these bridges suffered. And out of these, if you see, I'll show you, and a reconnaissance was done, not by us, unfortunately. However, we were able to visit 2000, right after the 2005 earthquake, thanks to Dr. Sarosh. Me and a few of my colleagues, we were there in Islamabad, and then we went to Balakot, up to Balakot the very next day. It was very chaotic at that time, but thanks to Dr. Saroj, we did able to go and see the damages at first hand. But we were recording for buildings at that time. We didn't come across any damages to the bridge. But this reconnaissance was done in 2007, and sorry, 2007, and it was published in 2011 in a earthquake spectra, and they have done a reconnaissance of around 90 bridges. So it was a huge amount of data that they collected, and what type of failures they saw, I'll show you. And using the ASHTO level of severity, they basically distinguished what kind of failures occurred. Because, like I said, our code does not have any vulnerability assessment code or design code. So the only code that is mostly used in Pakistan is that of the Americans. So the ASHTO code was the one that was employed. And most of the failures, as I'll show you now, you'll see. So these were the bridges, their um, um, types according to ASHTO. Some were critical, some were essential, and some were ordinary. And but these are just a few. Remember, they did around 90 bridges. Data was collected, and near the fault, as you can see, the slab bridge Balakot, which was around 70 meters away from the fault, up to 2 kilometers and even further away, was done. So this was the data that is already published in the public domain. And as you can see, uh, most of the bridges that sustained were in the no damage type. Now, that does not mean the bridge did not suffer any uh, damages. In the terms of limit state, as per design, they were in terms of no damage, but they still had functional damage, as you may say, that the uh, asphalt may have been, or the deck slab may have suffered, or it may have unseated. So these functions were not taken into account, but they were there. And as I'll show you now in pictures, you'll see that the bridge itself has not sustained any damage, but because of the other functional limits, the bridge is still unusable, which again is documented in previous earthquakes. And now the design codes do implement them in their design as well. But Pakistan does not have these, unfortunately. So this is the Balakot bridge. Here you can see the bridge itself has not sustained any extensive damage. It's still open. If you can see, a car is going over the bridge. People are walking over the bridge. But as you can see, the bridge has laterally moved because of the seating. Where the bridge was supposed to be, it shifted about a meter, which was very high. A meter is around what? I don't know. It's a huge difference of maybe 3 to 4 feet. So it displaced. So obviously, one end was basically cantilever, while one was still resting, because it's a pair wall system. Had it been a pile system, the system may have collapsed. There's no doubt in my mind. But because of it was a wall system, it shifted, but the other half, or maybe 1 meter, became cantilever at the end. Similarly, so I was just showing you the failures of the 2005 earthquakes, which were very similar to what is documented in worldwide in their previous earthquakes. So this is a drop-down case, and then impact pounding effects, as you can see at the joints that happened uh, because of the severity, unseating, as well as the pounding effect of the two spans, the damage to the girders or the main beams, as you may know, is there. Similarly, again, the abutment failure, you can see the entire abutment is basically failed. And again, here you can see it's a cable stayed bridge. But again, the end or the abutment is again, the foundation has sustained because of boulders basically striking the abutments. And then obviously the entire system is built out of masonry or blocks, so it's not able to sustain these impact loads, and obviously it becomes, the bridge itself, it's still unaffected. Because of the failure of the abutments, it's no longer usable. Here you can see again the bridge itself, it's there, but again the failure in the abutment has caused unuse of the system again. So the people have to use other ways of taking the needs from one place to the other. And because of a mountainous region, it's very difficult to do these things there. Now, these are the failures that we saw in the RCC bridges. This is a shear failure of the bridge, and that is because of the confinement of the bridge. And this is a Gari Dupta bridge, which is near Balakot, uh, which sustained a heavy loss of failures. Here again, like I said, most of the bridges at that area were colonial built. So you had most of these cable stayed type of bridges with steel or maybe wooden trusses. But again, they were mostly built by the Britishers, and they were still being used for heavy traffic loads. But again, because of the mountainous region, the impact loads because of the falling boulders caused extensive damage to the abutments. But again, if you see the bridge itself, it's intact. But as the abutment is destroyed, there's no way of using this facility any longer. Now, this is the complete failure of the bridge. And again, as you can see, it's a cable stayed bridge of a wooden structure. And I again remind you, this was still being, that was used for heavy trafficker loads. This is the pedestrian bridge, commonly failed again because of the cables that were anchored, the failure due to the anchorage, mostly these occurred. So from that, what we learned was, in terms of geotechnical, landsliding and slope instability. That was main of the factors that affected many of these bridges. Similarly, ground deformations or liquefaction was seen in many parts. Similarly, most of the bridges that were designed were up to 0.06. Remember, that is 6% of the given and the West Pakistan Highway Code. But the ground escalations, that peak ground escalation that happened they were in the range from 0.15 to 0.4. So it was a huge amount of movement these bridges saw. But since they were designed within the elastic range, and you can see most of the failures were at the entry or the exit points, or maybe where the reinforced concrete did exist. Obviously the detailing failures, because they didn't have account for these failures in their design or in their detailing, and that is mostly observed. So what is the main change that have occurred after the 2005 earthquake? The first thing that we saw, the major change in our codes, was from the seismic point of view, or the seismic hazard. The zoning map from MI scale changed to the PGA scale. So that was the first improvement, and Dr. Sarosh and his team are the authors of this. And they projected these PGAs, or the seismic design codes, for, I think, at that time in 2005, were for 475-year base period, which is the 5% that was. But nowadays, the code suggests that you have to take up to 2500-year period. You have to check if it's a critical bridge. So again, the code is being revised. I don't know. Dr. Sarosh may be able to provide us with the correct, but there is now again a change in the code, but it's still not in the public domain. And I think it's up to maybe up to 1500 years return period, or maybe up to 2000 return year period. Code is now published. But again, remember, this is for the building code of Pakistan, not for bridges. But we are using this uh, for bridges as well now. But again, for bridges, the seismic zoning has to be done at micro level. And again, this is truly deficient in that respects as well. And like I said, we need a 2500 return year period for critical bridges. So again, this is deviant in terms of bridge design. And after the 2005, like I said, we had two other earthquakes, 2013 and 2019. And in the Avaran earthquake, which is in Balochistan, generally it's a desert type of a terrain, plain terrain with mountainous regions. So there they have culvert bridges, short span bridges, less than of 15 meters or maybe 10 meters. And out of in the Avaran earthquake, 92 were damaged. Similarly, in the Maripur earthquake, which is again in the Azad Jammu and Kashmir area, the 2019 earthquake happened, and it was around 5.8 to 6, while the Avran was 7.7 magnitude earthquake. So again, you had the four main bridges which were leading towards the Azad Jammu and Kashmir and towards Maripur, they were damaged. So again, as we have seen that in because of the deficiency in our design code, in our detailing, we are still having these vulnerabilities in our system. So, and these are the few of the damage. As you can see, this is for the on the right. You can see it's on the bridge on Jatlan Canal. This is towards the Maripur. All the two pictures are from the Maripur. Unfortunately, I could not get any photographs for the Avran earthquake. As I said, they were very small culverts. So I think most of that has not been recorded. But these were major bridges. And obviously, as you can see, on the left hand side near the bottom left, you can see there is a car on the bridge or on the abutment, which was maybe traveling during the earthquake, and as you can see, it has collapsed. So now the next question would be, what can we do for future events? So obviously, as we know, the first thing is we need to upgrade or update our bridge design manual, because we can no longer use the 1967 bridge, West Pakistan Highway Code, which is called. We cannot use that any longer. So it has to be updated like the Building Code of Pakistan. Whether we adopt the ASHTO code or any other relevant code, it's up to the government to decide, but it has to be updated. But like I said, consultants and government offices are now using ASHTO with West Pakistan Highway Code. So I think would be the right time that we are able to update them. The second is, what is the current condition of these bridges? There are around 8,000 bridges on the national highway or the network across Pakistan. And we don't know a clear picture of what these bridges are, what type of their bridges are, what kind of condition they are in. So it's a very huge task that has to be undertaken. Now,
Excuse me, Professor Khan, if you can conclude in the next minute or couple of minutes.
yes,
that'd be great.
I'll do that. I'll do that. So, in order to answer that, what we did a project for the through Higher Education Commission Pakistan, and we did assessment of the Karachi bridges. And here you can see the road network of the Karachi bridge of the Karachi city. These are the total of 224 bridges that exist throughout Karachi or on the exit or entry points of Karachi on the district levels as well as in the entire Karachi. And as the strategy is for any assessment, first of all, we updated our seismic hazard mapping for Karachi. Then we did the risk assessment or the condition assessment of the bridges that are in Karachi. And using these two information, we then did the seismic hazard assessment, a vulnerability assessment using pushover or the non-linear or there is a software now available which is called Eller, in order to find out how many of these may damage for various magnitude of earthquakes. So this is the first step, that we updated our seismic zones for Karachi. And here on this 475 return period, you can see the location of the bridges, and you can see most of the bridges are in the red zone, where the ground acceleration is up to 0.3 to 0.35 G. And remember, most of these bridges are designed only for 6%, 0.06 G. So again, and this is the variety of bridges that exist in Pakistan, or only in Karachi. Here you can see we have pile cap, pier types, single steel types, various types of abutments, various types of superstructures, whether they are girder bridges or maybe box girder bridges, and so on and so forth. So in order to create this condition assessment and inventory of the bridges, that is the first step, we had a software developed at NAD, thanks to Dr. Sarosh and Rafiki Saab. It's called as a Bridge Database Management System. Here we can not only take the physical features of that, but any condition that may be prevalent on the bridge can be recorded in this software. And depending upon what is the condition of the bridge, it will rank that bridge accordingly, whether its repair should be done immediately or they could tie up with when the maintenance or the repairs can be done at a later time. So it has 4 modules. The first one is the inventory module, where all the data is collected either through drawings, through design, or through photos or graphs or whatever is available. Then inspection is done of each bridge physically, and using that data, we can then compute what is condition. And as you can see, this is the prevalent conditions of bridges in Karachi, where we have a lot of bridges that are in need of repair or maintenance. Unfortunately, in Karachi, these structures are not taken ownership by the government and themselves, because we have around 6 local governing bodies in Karachi. So most of these bridges are either at the interchange of these bodies, or maybe within that municipal area, but none of these have any maintenance or repair regimes. So they are usually built and forgotten.
Professor Khan, yeah, if you can conclude now.
Yeah, I'll do that. So we did using that data with the condition, we basically then develop analytical models, and using the fragility curves, we were able to use a software called the Eller, and we were able to find out what were the probability of failures of these bridges with their extent of damage. If For example, 1,000-year return period, which would be a 6.5 magnitude earthquake, uh, as you can see, mostly would be within the some to extent damage category in most of these bridges. So again, I think I'll conclude here. I will not go into the retrofit part. So as you can see, assessment requires a lot of detective work. And for us, it's starting from scratch. As you can see, we have no code available which can guide us. So generally, we used to take, or we still take, uh, from other codes that are prevalent in the developed worlds, that is ASHTO or other country codes. But ASHTO is mainly being used, but it's not document of Pakistan, unfortunately. So it's a mix and match in our design still at that level. So obviously, I'm hoping that if an earthquake does happen, which Dr. Saroj says it may happen, there would be extensive damage to our infrastructure, especially bridges. And I think our municipal bodies are not ready, or will not be ready to handle that kind of magnitude failures. Thank you very much.
Thank you, Professor Khan. We can take one or two questions from the audience, especially from the people who are from Myanmar. And Mr. Somyant, you might be able to see the audience there physically, and you can point out if there's any question.
Sorry?
Was there a question, Mr. Somyant?
Uday, do we have enough time? Because I think Dr. Rashid has taken a lot more than
Yeah,
his location.
yeah.
I think, even though there
I
could
think
be a lot of
we should
questions.
move
Yeah.
on.
Yeah,
Yeah,
I think,
yeah, you're right.
Yeah.
So I would like to move on. We're running a little bit behind schedule. The second speaker is from the American Society of Civil Engineers, Dr. Sreenivas Alampalli, and he's the senior principal transportation at Stantec. That's the name of the engineering company in Albany, New York, in USA. And Dr. Sreenivas Alampalli is an international recognized expert in structural health monitoring, bridge engineering, and transportation infrastructure asset management. He's got 30 years of experience in research, asset management, and he is he has built strategic public private academic partnerships to ensure safe, reliable, and cost-effective infrastructure using sound asset and risk management procedures. And he was recently inducted as a ASC distinguished member, and for his recognizing his subject matter expertise in this area. And in addition to his previous work leading to the New York DOT's structures management, he's successfully managed more than 100 research projects and authored more than 250 technical publications, including 6 books related to infrastructure. His topic is about the recent earthquake in New York. It's on the post-seismic bridge inspection guidelines, implementation, and lessons learned from the recent earthquake in New York. Go ahead, Dr. Alampalli.
Thank you, Dr. Singh, and thank you for giving the opportunity to present. And good afternoon, everyone. I hope everybody can hear me well. This work is based on a research project we initiated in 2010, almost 15 years ago, and was completed in 2012. This was used since then in the New York State DOT and formally adopted about 5 years ago. I'm going to give you some brief details about this project and where we are with how we adopted it. If you are interested in more details, you can always contact me and I can send the final report as well as the adopted guidelines. First, I would like to acknowledge 2 people who contribute to this presentation. Mr. Jerome O'Connor, who was the co-PI of this project, who was the actual project manager for this project when we implemented 15 years ago, and Paul Campisi, who contributed some slides on how DOT reacted to the recent earthquake. Like Dr. Khan mentioned about bridges in Pakistan, there are a lot. New York State has about 20,000 bridges. Of course, they come in all shapes and sizes, starting from complex bridges like this, which are recognized all over the world, to uh, uh, regular bridges like this, simple truss bridges or with concrete slab and steel girders, which I call them bread and butter type of bridges. As all of you guys know, bridge network is a backbone to transportation network for mobility, reliability, as well as economics. So having them certified after a major event is very important to make sure they are safe for public as well as for ensuring emergency responses after any event. So what we observed in recent earthquakes around the world shows the importance of having a procedure in place. Again, 96% of the structures being very simple structures, such as these I'm showing here. What we are interested in looking at the vulnerabilities of these kind of bridges and how do we react when with respect to this kind of bridges when an earthquake happens. Again, visual inspection and other programs are mostly reactive. That's why in New York State Department of Transportation had for the last about 25, 30 years a very good proactive vulnerability program. DOT looks at a lot of hydraulics because that's the number one cause of bridge failures. So DOT has very good post hydraulic events, how to react. We have a very good plan, and organization knows how to react very well. Similarly, DOT also sees about 200 bridge impacts every year, and they have also a very distinguished program on how to react when we have an impact. At the same time, seismic events are not common, are not often in New York. So we have New York has a very common sense retrofit procedure available during rehabilitation, but New considers all the very good seismic design procedures. At the same time, as you know, earthquake can affect not only a small regional area, but can affect the whole state. Depending on magnitude and where it happens. So New York State is in a low to moderate risk, even though low probability of occurrence due to high consequences. So we initiated this project in 2010 to establish a procedure on how we want to react when an earthquake happens. As I mentioned, we do have a long history of earthquakes, but mostly, relatively small. Even though we have about 550 recorded earthquakes, most of them are low to moderate seismicity. these gives some examples of recent earthquakes. I'm going to sort of talk about this 2024 New Jersey earthquake, where M4.8 felt in New York State, but essentially we really didn't have big damage. So when the project started, these are the deliverables. Uh, we wanted to have an earthquake response plan. We also want to have a database application for prioritizing inspections, the bridge inspections, depending on their vulnerabilities, as well as probability of damage and importance. We also want to come up with a post-earthquake bridge inspection guidelines, guidance on interim repairs. We also want to have a training for all the employees who will be involved with it, and then of course a project final report. These are the components we considered when we started working on this emergency response plan. Any emergency response plan to be actively, be useful, you need to have formal policy and documentation. It has to be readily available. We need to define the roles and responsibilities, when to use it, or what to do, who will do it, and why we should be doing it. We also want to use the deploy resources effectively whenever we have any event. A lot of these apply to any emergency response plan, but we use them in with seismic considerations in this project. We also want to take advantage of the organizational structure if you want the post-response plan has to be effective. We also want to have clear lines of responsibility. Well, at the same time, our reaction has to be depend on the type of magnitude. So we want to have different levels of response. And we also want to define how a response will be conducted, what first responders and bridge inspectors should look for, how to report the findings, and how do we want to follow up. Then, of course, naturally, we want the training and also we want to make sure that the right resources are needed. This is the final report. This was published by MCER in Buffalo, New York. Again, this is available online. I do have a link in the presentation. If you just Google saying post-earthquake bridge inspection guidelines for New York, and you'll get this will be one of the first items you see. And this is the final report. As I mentioned, it does have talks. We do want to give some basic guidelines about earthquake. Somebody who really doesn't know much about the seismic engineering want to come and look at it. We want to give some idea what earthquake principles are and also how the bridges perform. And then we talked about emergency response plan based on what the guidelines I mentioned before. And then, of course, some technical guidance and references. So general procedure we developed based on in this project was it starts with a USGS notification. As most of you are involved with seismic activities, you know that anytime there's an earthquake, United States Geological Society issues a notification immediately. So as soon as it happens, the headquarters in New York State Department of Transportation decides if a response is needed or not. We want to make sure that it's centralized and we use uniform procedure. So the headquarters decides on what to do. In New York, has about 11 district offices are called regions, and we have a headquarters. So, and the response depends on magnitude of the earthquake, distance to epicenter, and of course also based on any observed damages. So the headquarters who has the database of all the bridges, all the condition data, and all the vulnerability information, they take that list and prepare the list of bridges should be inspected by engineers. Each region and each who will dispatch the staff. It could be in-house or it could be consultants for preliminary look, appropriate action needed, and documentation. Then, if needed, we dispatch additional staff or the experts for detailed inspection. And of course, the inspections are prioritized based on local knowledge, vulnerabilities, and criticality by regional people. Because even though from headquarters we come up with a list, it has to be modified and it has to be flexible depending on the local knowledge. Based on the assessment and severity of damage, and these are all taken into account when inspections are done. And as soon as these assessments are done, temporary and permanent repairs will be initiated. So USGS notification looks like this. So what we told all our engineers involved with is to subscribe to USGS notification. Our headquarters office, people who are involved with structures and the vulnerability program also registers for this. So as soon as an email or text notification comes, everything starts. We came up with 4 levels of response based on the magnitude. As soon as the regional engineer receives the text message or email notification from USGS, first thing they look at is what the magnitude of earthquake. If it's greater than 3.5, then we start in response. If less than 3.5, we felt that nothing has to be done unless we hear any reported damage. So if it's more than 3.5, then response level gets initiated and affected residents does a preliminary bridge damage assessment using the local people and our highway staff who are readily available. If damage is found, then it goes to the next level. So again, if response level is between the 3.5 to 4.5 and impact damage bridges found in the preliminary bridge damage assessment and seismically vulnerable bridges in 40-mile radius are looked at. And if it is 4.5 to 5.5, we look at 60-mile radius. If it's more than 5.5, then at least 80 miles to more radius, depending on the damage. We also will conduct a aerial reconnaissance survey, and based on that, if 80-mile radius has been extended, it will be extended and look at vulnerability policy. Then based on if any damage are found, they are flagged following the DOT policy, and additional investigations will be made. The first level of response, because 11 regions have a lot of staff, highway staff, not only bridges, if any highway gets affected also, if people cannot travel. So what they do is as soon as they need to go and look at response, they take the car and they drive with simple, I'll show you the form we have for preliminary damage assessment. Idea is to look for simple damage like this, is there any approach problems, is there any simple superstructure damage, substructure damage, is anything. Essentially what we are looking for is observable damage so that decisions can be made like if it's really bad, they can close the structure and then ask for more help. If not, they can move on. And the form is very simple. For each structure gets one line in this preliminary bridge damage assessment form or first level response plan. As you can see, it just talks about what the bridge ID and the feature carried, feature crossed, and what time they came. And they look at the different things. Is bridge open to traffic? Is anything collapsed? Is the bridge any apparent bridge damage? As I said, essentially they're visually looking. They are not really expert bridge engineers. They're regular engineers or technician type of staff. What they are looking is just to make sure that nothing major happen. And once they have this form, at the end of their route survey, they'll send it to their district engineer, and he looks at the reports and decides what to do from here. Once they also look for any initial reports from the public as well as social media, because lately with social media you hear first even before we deploy anybody else. So we take all those into account. We also, New York State also has excellent seismic vulnerability program, which looks at the mode of failure and other geological vulnerability and other aspects of it. We also look at the structural condition, criticality, and all from the database. We're looking at all these. There's a special post-bridge inspection will be issued. What they will look for here is, spalling and pounding and those kind of other issues they will look at. And again, depending on type of failure, like geotechnical engineers or experienced inspection team leaders or other specialized staff will be sent, and they will look at it in much more detail. As you can see, they know exactly how the capacity of the structure is structure. Capacity of structure will depend on a lot of these factors. They know exactly how capacity of structure changes based on the damage. They can make expert opinion and then come up with what to do immediately, whether we need to close extended or can we do some simple repairs quickly. Those kind of decisions can be made, and then we can prioritize the structures. When it comes to repair strategies, of course, we just come up with for each type of for approach, pier columns and all, depending on type of damage we got, we did give some guidance on what kind of repair possible actions can be made and what kind of retrofit system can be used quickly. And again, this is for the, I'm just going some examples here. If you go to the report, you can see all the details for different components. Then at the end of this project, we had a one-day training for all the headquarters staff and all the regional bridge engineers and also consultant community. We taught them about the procedure, what are the responsibilities, USGS notification, prioritization, communication, strategies and documentation. All these were given. We took their input and modified the overall program little bit based on the input we got. Finally, using this report, New York State developed their guidelines. It took a while for them to finally come with official policy. It happened in 2020. And again, they essentially followed very similar whatever we suggested, except when earthquake is more than 5.5, they decided to initiate the statewide transportation information coordination center so that they can coordinate better, because it means you have a wide area is affected. So they want to have much better control over that. Again, these are the guidelines. So how is it working? That's more important, right? So that's why I just want to give you this case study on how it happened. Recently, last year, we had a 4.8 magnitude earthquake in New Jersey. Epicenter was about 48 miles from New York City area. As soon as it happened, we did initiate the overall system. About 1,000 bridges were inspected, but no damage due to event was noted. Again, as I said, even though you look at a lot of bridges, they're all very preliminary assessment, very quick visual inspection. So again, I will just give an idea how the whole everything went. About 4.7 for 4.8 earthquake initiated as soon as the USGS notification came. The headquarters looked into our seismic vulnerability manual. Based on that, again, Dr. Khan mentioned about different aspects. So this is the vulnerability program. It looks at different components of the structure. This all is already in the database. So these are different goes into based on that, it prioritizes what structure should be inspected in the given area. So essentially, we input what the epicenter and where the GPS coordinates of the epicenter. Then it automatically generates the list from the database and comes up with the overall list of by each region prioritization it comes. In this particular case, the earthquake falls in this category. So about 60 miles radius we have to look at. This gives you an idea, the area of, it covered about 4 different regions in New York State. They came up with the structures. Again, as you can see, they came up with a lot of structures. About 1,100 were group 1, 1,300 were moderate high, 39 were moderate low. Overall, the total structures in this region were about 3,675. And they generate the lists, and then all the regions are notified. We also use consultant teams when we need to inspect bridges. So consultant state teams are notified, and lists were distributed to regions for deployment of teams. At the same time, one of the aspects which happens is once they start inspecting, the aftershocks come too. Some of these aftershocks are also big, initiating. If we already inspected the bridge, what do? Are you going to go back and inspect again? That was an issue because this 4.0 means you need to go and inspect about 40 miles radius again. So this is another sizable event. So we have to rerun some of the numbers and double check the list to make sure that some of these may have to be, if they already looked at, they had to be re-looked at. Then other aftershocks came with less than 3.5, so we didn't have to worry about that. As I mentioned, initial review and assessment, custody visual inspection to identify unsafe bridges, no work zone traffic control or special access required. Mostly binoculars are acceptable and should be used only if available to identify what are the is there any perilous conditions in need of closure, is there any safety issues, and do we need to do more in-depth inspection so that experts can go and do the inspections. We really did not find any major issues here, but at the same time, they did find some spalls and some critical findings, but the inspectors were not sure if it was there before or it happened during the earthquake. So that was something we need to resolve. They do have headquarters and regions do have access to the old inspection reports, so they were able to go back and verify are needed, but it does take some time. And they also found that access issues over railroads. If you have in US, railroads are owned by private companies. So if you want to access above that, you need special permission. So that was one thing we were trying to resolve how to do it in case of this response that was not thought well. And also no written inspection needed. If they have an aftershocks, do we need to go back and look at it or not? That was something was not very clear. Essentially, as I mentioned, there are 4 different regions. Overall, about 442 bridges were looked at, and there was no damage. Again, as you can see, this is a small, relatively not a very high magnitude earthquake, so it went well. In conclusion, a response plan was developed closely working with the Department of Transportation. It incorporates DOT organizational structure. It incorporates existing resources, both software and personnel, used in few cases before the policy was adopted. So far, it seems to be working very well. Besides technical and structural, social issues also dictate what inspections are required. Plan will keep improving based on the responses we received during the last earthquake. That's all I have. If you have any questions, I'd be glad to answer. Again, as I mentioned, these reports are publicly available. You can go and take a look at it. If you have any questions, feel free to send me an email. I'll be glad to answer. Udai, I'm done.
Sorry. Yeah, we are open for questions now. I have a question. I mean, how and this applies to Myanmar. How easy it is, because you have a very good Department of Transportation in the state of New York. So how does it translate to countries such as Myanmar for them to do similar things like what you're doing?
As I mentioned in the very beginning, any plan you come up with has to take advantage of the organized structure they have. It has to be modified to make sure organized structure in Myanmar is taken care, into consideration. Again, as I mentioned, the preliminary assessment does not require experts, as long as somebody with some engineering background who understand different components of the bridge. So we came with a very good training manual where actually all the photos for different types of damage. Look at even somebody is a highway engineer, not very familiar with the bridges, should be able to look at the report and should be able to come up with preliminary assessments. Of course, if you find any damage, then you need an expert. You need to identify them beforehand so that when earthquake comes, you're not scrambling to get an idea who should go. I think if the question is if organized structure is not ready, then maybe they should consider some of the academia and other engineer consulting companies. They should maybe have in their list so that if something happens, they can immediately contact and make sure that they'll get the required help.
Thanks. Any questions from the audience? Okay, so I think there's a question online here in the chat. It says, what were the key lessons learned from this earthquake response? What were the biggest challenges faced during the implementation of the inspection guidelines? And how should Myanmar overcome such challenges in its implementation?
Again, New York has a very good regular bridge inspection program. Like what I mentioned, we have been doing bridge inspection for the last 40 years in New York. So we have good organized structure. Main issues we found, as I mentioned in the last slide, is if somebody goes and sees the damage, uh, making sure that the damage didn't happen during the earthquake, because if it was the previous damage, not because of the earthquake, you really don't have to do anything. So having access to the inspection reports and somebody quickly go back and look at, having the online database availability for all the inspection reports is going to be very useful. And then the aftershocks, that's something we really did not think very well. If you have a major earthquake, aftershocks can be very big also. If you already inspected, let's say, under structures, you have to go back and look at them again. That's something, we didn't think of. We learned about it, and that's something we are trying to accommodate now.
Thank you. Any other questions? I don't see any others. So we can, if we don't have any other questions, let's move on to the next speaker. Thank you very much, Dr. Alampalli.
Thank you.
The third speaker is from Engineers Australia, Professor Hong Hao. He's a professor at the Earthquake Engineering Research and Test Center in Guangzhou University in China, and also the John Curtin Distinguished Professor in Curtin University in Australia. Professor Hao's research interests are structural dynamics and its applications to structure protections against earthquake, blast, and impact loads, as well as structural condition monitoring. He's published extensively, and his research results have been included in many textbooks and design codes applied to many construction projects around the world. And he has been named multiple times as the annual Australian Research Field Leader in Civil and Structural Engineering, ranked #1 in Structural Engineering in Scholar GPS. He was the president of the Australian Earthquake Engineering Society and president of International Association of Protective Structures. And Professor Hao has received over 60 research awards, including Nishino Medal in 2022 and Charles Bob Medal in 2019. Professor Hao will be talking about responses of prefabricated segmental bridge structures subjected to spatially varying earthquake ground motions. So Professor Hao, go ahead, please.
Thank you, Dr. Singh, for your kind introduction. In this presentation, I will briefly report or introduce to you some of the work I've been doing in the last probably 40 years, mainly relate to ground motion spatial variation modeling and its effects on structures. And we know ground surfacing at any two structure supports, ground motion inputs are not exactly the same. That is, say, ground motion spatial variation is inevitable because when a seismic wave propagates, it have a different, goes through different paths. So affected by source effect, pulse effect, or local site effects. And those are some examples. And on the right is recorded ground motion at the Smart 1 array in Taiwan. You see they have a separation distance about 200 meters. And on the right are the recorded ground motion in China. In separation distance is about 100 meters between each two records. So the variations of those ground motions are very obvious. And the spatial ground motion spatial variation will cause very different structural responses because they will excite some asymmetric modes. For example, for arch structure, for arch bridge, the fundamental vibration mode is asymmetric. If we use in the structural response analysis, we assume uniform input, this asymmetric mode will not be excited. But if we consider ground motion inputs which are not exactly the same at the two supports, those asymmetric modes will be excited. We know that dynamic participation coefficient of first or fundamental modes in most structures usually is more than 90%. So if we neglect or if we cannot excite this first fundamental asymmetric modes, we might substantially underpredict the arch response. They also cause relative displacement, as we see many in most, in basically all major previous earthquakes. If those relative displacement were close up, if the separation distance is insufficient, corresponding, or if they separate that they move away from each other, if seating length is insufficient, we get the unseating damage. It will also cause a torsional response. Let's say if we have the structure is symmetric, if we assume input is symmetric, we're not going to get this torsional response. But we can see this kind of responses in all the major earthquakes. So those are some examples: unseating damage, and we observed in various earthquakes, and the pounding damage between the bridge girders or adjacent bridge structures, or torsional response. So in fact, ground motion spatial variation is a fact that has been recognized 60 years ago. The first research or publication was in 1965 by Bogdanov, and our earthquake engineering, father of earthquake engineering, Newmark, also start to consider, did some study since 1969, and his last paper published with Newmark Hall, Morgan, the students, in 1983. They start to consider try to model ground motion spatial variations, and many others, such as now we all use STEP 2000. In fact, in 1980s, when STEP 4 came out, already has a capability to model ground motion spatial variation in the structural response analysis, and those are the commercial codes. Some are non-commercialized codes like NIAPS by Joe Pengen. Now it's quite popularly used in California in bridge design. And they started in 1980s, already started to consider ground motion spatial variation. But there are challenges in the most previous ground motion modeling, ground motion spatial variation modeling. They only consider the wave passage effect, that is the traveling wave, seismic wave that is, for example, at the A1, at one ground motion, and one support A1, if a wave is traveling to the another from left to right, they just put a time delay. That is, say, we only consider the seismic wave passage effect, but neglect loss of coherency. But we saw we have this phase shift or loss. We have this phase shift, but because the seismic wave travels in heterogeneous medium on different sites, they also have loss of coherency or loss of correlation. They will not be exactly, in other words, they will not be exactly the same. But those loss of coherency effects are mainly neglected in most of the studies or earlier studies. And the most, I would say, most major design codes recognize the importance of considering earthquake ground motion spatial variation, and they all said we should consider this, but most of them do not provide, because many challenges. Most of them do not provide detailed analysis or design procedures. For example, the Chinese design codes, they said we should consider seismic ground motion spatial variation, especially for the large long-dimensional structure. But that's it. ASHTO, the ATC codes, Japanese codes, Euro codes, Euro codes and Italian codes probably are the only two design codes so far give some analysis guides, but I demonstrate to you they do not actually, might not give good reliable predictions. And in other codes like ISO and many others, and same. And So the many codes like Caltrain codes, for example, they put says you need to provide sufficient seed length, and and also the span, the vibration frequency of adjacent spans, the ratio should be larger than 0.7. Or ATC codes, Taiwan codes, or Japan codes. Japan code, all these codes only the required seed length is say depends on the span length and the structure or bridge height or pier height. So you might say implicitly consider, if the span length implicitly consider ground motion spatial variations, because ground motion spatial variations very much depends on the separation distance. And the Japanese codes, it's probably the only one they consider the soil deformation, consider soil deformation in estimating the required seed length. And but those are the very simple, straightforward calculation, and obviously they are insufficient to prevent unseating from occurrence. Desroch and Fenves, they did some studies. They just use a very simple model as model the two girders, two spans as a single degree of freedom system, and they calculate what is the required stopper or restrainer to prevent unseating. But in this study, they did not consider ground motion spatial variations. We also did some work, my students and my PhD students before. We did the numerical simulation and the shake table test as well, and also suggested to use frictional pins to put these frictional pins there for these diamond shapes put in there to here we use just a chip memory alloy to stop unseating from occurrence. And so in practice, you can see if you go to Japan, you go to some high seismicity area in China, you can see many bridges. Those are the very simple way. There is no detailed design guides, but engineers just provide. For example, they extend the seed length, or use the stopperness, or use here like you use this restrainer. Use different type of restrainers and to stop unseating, or use a modular. UC Berkeley, I think they invented this modular expansion joint maybe 20 years ago. You can make it very wide. First, you can accommodate for thermal expansion, larger thermal expansion, or at the same time you prevent pounding without affecting the smooth travel of traffic. So use rubber. Some researchers or some practice engineers put the rubber in the expansion joint to mitigate the pounding damage. But the problem is you put the rubber there, it will mitigate the impact force or pounding force, but it actually reduce the separation distance or reduce the gap. So the pounding might more likely to occur. So there are many different ways in practice people just use it, but there is no detailed design guides. And I said Euro codes and Italian codes. Italian codes a new one, just released one. They are probably the only codes to provide some guides and to do the calculation design analysis. First, what they do is they use the design response spectrum and to do the analysis. This is uniform design response spectrum to calculate the dynamic response that is the bridge, so still the same as traditional analysis methods. And then they assume two sets of ground motion special support movement. They calculate DG, the peak ground displacement, based on the design spectrum, and multiply this DG by square root 2 to amplify it. And then at the different supports, they have one set is in-phase ground motion displacement set A, and out-of-phase ground motion displacement set B. So in this one, at all piers, at all supports, ground movement is the same, in same direction, but a different amplitude. In this one, ground motion at the adjacent supports that move in the opposite direction, but have the same amplitude. So they have this set A and set B, and then they calculate dynamic response based on the uniform input, and then they have a quasi-static or pseudo-static response, and based on the set A ground movement and set B ground movement, then use SRSS to combine them. So this is straightforward to use, but obviously the assumption of ground movement is kind of arbitrary or highly idealized. And also we say for the seismic response is a dynamic response, its inertia effect is critical. But now, when they do the dynamic response analysis, still assume uniform input. So that would introduce some inaccuracies in the response prediction. So to verify this, we did some analysis, use a very simple bridge model. Say its span length is 17 meters. We have a few spans do the standard analysis. So we do the calculation, follow exactly the Euro codes, and say we, based on the design spectrum, and we calculate the dynamic response, and we use the set A, ground motion set A, we calculate this quasi-static response, and the ground motion displacement set B, we calculate another set of quasi-static response, then we use SRSS, combine them together. And then we also did the spatially varying ground motion analysis. That means we simulate the ground motion multiple inputs at different supports. So we use this input, directly input to the structure. We calculate its response. We can see those are the errors. And so we can assume it's, say, ground motion spatial variation is highly correlated or intermediately correlated or weakly correlated. Wave propagation velocity varies from 500 meters to 2,000 meters per second. And the error could be, some is okay, error is small, but some errors is over 70%. So that and errors also occurs randomly. That means those design approach, it's very difficult to generalize, and it's difficult to predict what is inaccuracy or error it might introduce to the structural response. So that will impose a great challenge for the safe and economic design of the bridge if we follow those straightforward code guides. And similar observations also reported by some researchers from Bristol University in UK. They also did some a comparison and draw the same conclusions. So that is what we would say is, after 60 years of effort, and it is still a challenge to reliably design structures to resist spatially varying ground motions, and that the damage Ava Bridge collapse in Myanmar earthquake this year. That I think the ground motion spatial variation will contribute to this unseating of the spans that cause this damage. So there's still a lot of efforts we need to do. So to quickly summarize what we can do, there are basically many 60 years of research effort. And what we can do is, first we need to model ground motion spatial variation. How can we model it? We can do it in the time domain. We calculate what are the auto covariance or cross correlation, cross covariance, or do it in the time frequency domain. We calculate power spectrum, cross power spectrum. We define coherency loss, coherency function, and the phase function. Or of course, we can define its envelope function to define the ground motion. So basically, now most people to model ground motion spatial variation use coherency loss function. This coherency loss function consists of basically two terms. One is coherency loss. That is amplitude of loss function. Another one is the phase shift. Phase shift it depends on the apparent wave velocity. That is how we can define apparent wave velocity is a big challenge. What we can assume, for example, if we assume apparent wave velocity, we assume as the seismic wave enter into a site at the angle alpha, and if we assume the wave consists mainly of a shear wave, then we can use the site shear wave velocity as to define what is apparent wave velocity. So just the shear wave velocity divided by cosine alpha. And two extreme cases, if it's horizontally incident, so the apparent velocity just equals shear wave velocity. If it's vertically incident, so the apparent wave velocity is infinity. That means there's no phase shift. The wave seismic ground motion will arrive at multiple structure supports at exactly the same time. But those are highly idealized. First, we don't know. It's very difficult to determine what is the incident wave, incident wave angle, and also the site is not homogeneous. And the seismic wave consists not only shear wave but also P wave and even surface wave, the Rayleigh wave, lava wave, and also because of non-homogeneous inhomogeneity of the site will cause wave refraction or the reflections. So that is some study I did many years ago. We just use FK analysis and use actually recorded ground motion at a small one, so we can see the ground motion, the wave velocity actually is it depends on the time and also depends on the frequency. So that is a big challenge at the moment. I would say we don't have a good solution yet. And so in the research community or in the design community, people still just assume, for example, shear wave velocity divided by assume a cosine incident angle. That is the current practice. And for the coherency loss, and there are many studies. So we have, say, theoretical models based on the wave propagation in random field. And so those provide some theoretical basis of how the ground motion would vary. But it's difficult to determine those parameters because the site is basically also itself is random and or semi-empirical model. And so and also we also did some work to consider a site, different sites. We assume the wave comes to the base rock and then it propagates up to the ground surface. at different soil layers. So we derive the coherency loss functions, considering what is so shear wave velocity at density has certain probabilistic variations. So we can derive this semi-empirical model. But most model so far we use is empirical model. You can see those are the seismic arrays, seismography arrays around the world, many in United States, some in China, in Japan, and has many records. Based on those records, we just did a survey, literature survey. We can find about around 100 different types of empirical coherency loss models. And those among this 100 empirical coherency loss models, some of them are okay, good. Some are actually not good. So we found the problem is that anyway, there are many those models. Some those are the models I promoted. I suggested based on the analysis of Smart 1 ground motions in Taiwan. But the problem is we have so many those coherency loss models. So you look at the publications in design practice, in research, and people just rather randomly select a coherency loss model and without any guides. This again, it becomes a challenge that might lead some unrealistic predictions of ground motion spatial variation, which then will affect the structural response prediction. So for this reason, we recently did some work. We just collect all the available coherency loss models and at the different site conditions, and we just do the statistical analysis. We get its mean value and standard deviation, and so those work is just recently published. So what we do is at least we give engineers or researchers guides and say you can choose the mean coherency loss functions for a particular site condition, or you can choose the mean plus one standard deviation or one minus standard deviation. So we have, in a statistical sense, you have a range. You can define a range to calculate the structural response, how this spatial variation would affect the structural response prediction. So those are some recent works. And for prediction of ground motions, of course, we basically we predict the ground motion on the rock side, and base rock side we can use the Roos-Pengine model or filtered Tajimi-Kalai model, or use based on the design spectrum of different countries or different regions, or we just use the statistic attenuation model, ground motion geophysics models. So once we get the ground motion and spectrum on base rock side, so we model assume it's a coherency loss spatial variation, and then we at the different site conditions. With a different site, we calculate the wave propagation through the site. Then we can predict the ground motion on top of the surface, which can be used as the supports to the structures. And so if it's a flat site, that is the work we did. I did a long time ago in 1989. So we can do the prediction, follow this way. Or if we have this uneven site, we can also do the prediction. Or if even it's a subsea site, now we have a lot of subsea structures. Please note there are some one in California, another one in Japan, subsea seismographic stations, and the record indicates the ground motion at subsea site is very different from those onshore site, even at very close location. This one is in California. If you have a record here, they are very different. So we need to consider the soil influence, the effects of soil, and not soil effects, influence of water on the ground motions. We also did some work, so we can predict the subsea ground motions. So And for the structural response analysis, of course, we can do the stochastic analysis. Those we can because of timing, I do faster. Just to emphasize the ground motion spatial variation. Actually, it's very much depends on a parameter. It's not only depends on the vibration, spatial variation itself, also depends on the structural vibration frequency. So it depends on this vibration frequency times separation distance divided by apparent wave velocity. So when this FD divided by V apparent equals 0.5 or 1.5, that represents the ground motion at multiple supports and the vibration modes are out of phase. So we get the response basically is a minimum response. It's out of phase excitation. If they equals 1 and 2, we get it's about the same. It's in phase excitation, so it's more like uniform excitation. But of course, we need to consider coherency loss, so it's not exactly at 1. So and also look here is frequency is a very important parameter. So if the frequency is large, if you have a very stiff structure, it's more sensitive to the ground motion spatial variation. And if the apparent velocity is small, or wave transmitting at a soft soil side, structure is very stiff, you have a larger span, then ground motion spatial variation effect is the most critical to the structural responses. And so we also can do the numerical analysis. This is work we did many years ago for this elevated aqueduct in China many years ago. And also on the bridge, we can predict and have a detailed model to calculate the pounding, unseating response. So we can do the detailed model if we have the proper, suitable, reliable ground motion input. We can do this kind of analysis and the response prediction. And those are the unseating, pounding.
Excuse me, Professor Howe. I think we are running out of time. So if you can wind down quickly.
Okay. We can also did a lot of tests. So I quickly show those are some tests we done. And recent work we're talking about the use sustainability, durability, and resilience development. And those are the testing. And those are the segmented use geopolymer concrete with FRP reinforcement, FRP tendoning. And so those are the recent work. It's a geopolymer concrete bridge structures with FRP tendoning. So it's a sustainable and durable structure. We prove it can be applied for the structural response. Have a similar structural response resistance capacity can be used in the bridge constructions. So those are cross-fault tests and also numerical modeling. And so because of the time, I'm not going to talk in detail. Just want to emphasize earthquake ground motion spatial variation is real, inevitable, and we have spent the 60 years a lot of significant resources doing research on it, but still a lot of work needs to be done. And so that is with that I conclude my presentation. Thank you.
Thank you. We have time for maybe one question. Okay, I have a question here on chat. It says, according to your experiences, what lessons have been learned from past earthquakes regarding segmental bridges. How should post-earthquake inspections of segmental bridges be modified to account for spatial ground motion effects?
Segmental bridge, I think we have a segmental piers or a segment girder. And basically, if in general, segmental bridge is most vulnerable is the joints. We did many studies. We tried all different type of joints. Either you have energy dissipation or without energy dissipation, because normally segmental bridge you don't have the reinforcement continuity, so the energy dissipation level is small. That is one thing. And second, for segmental bridge, it's relatively flexible as compared to the monolithic structures. So it has a relatively larger displacement. So the force might not be the force governed in the design, might be the displacement governed for the structural response. So that might make it, you might see more pounding or unseating type. So for the inspection, I think it's same if it just says the post the earthquake inspection or the condition monitoring or condition inspection. I'm not sure which you refer, but we can do the now. Of course, people still use the visual inspection, but now non-destructive type inspection. You fly drones to the we can use the UAV to easily to get a lot of photos or even to measure the displacement or response deformation. And so inspection-wise, I believe it doesn't matter whether it's a segmental bridge or the traditional bridge. You just look at, but you look at the joints. Joints is the most vulnerable area for the segmental construction, and its unique characteristics, say no energy absorption capacity and low vibration. Relatively smaller stiffness.
Yeah, thank you very much, Professor Howe. Really appreciate your talk. We are ready to move to the final speaker. And he is from the Nepal Engineering Association. Is engineer Bipin Kumar Gautam. He's a structural engineer and director at Resilient Structures Private Limited in Kathmandu, Nepal. And he's also currently serving as an infrastructure specialist at the World Bank, Nepal. He played a key role in Nepal's post 2015 earthquake recovery, leading technical teams in the reconstruction and retrofitting of private houses, public buildings, and heritage structures. So, and his expertise has been central to advancing resilient construction practices through the development of comprehensive technical training curricula, manuals, and guidelines in the housing sector. So we'll let him speak about integrated technical approaches for private housing reconstruction and retrofitting in Nepal. Engineer Bipin Gautam, you're on. Thank you.
Thank you, Dr. Udai. Before starting my presentation, I'd like to thank ACECC and FEDMES for having me here to share our experience after post 2015 Nepal earthquake. So basically my presentation is not much technical as presented by previous presenter or speaker, but I hope that I'm sharing our experience on the private housing reconstruction, so that might be useful for the FEDMES and the Myanmar government to execute the reconstruction work, especially for the private housing here in Myanmar. And the private housing is always a challenging work because for the public building and other infrastructure, generally the government take a role to do all these activities. So for the private housing, every private housing is a individual project, and we need to deal with the public to do the reconstruction work. So I'm going to focusing on the reconstruction and retrofitting of private housing. So how we we make a how we did the technical approach during the reconstruction work. So this is my brief outline. I will not going into this. Then before going to my presentations, I have a quick overview of this 2015 Nepal earthquake. So you can see a couple of map here. On the left hand side, you can see the map by USGS where the earthquake was struck, like having a magnitude of 7.8 on April 25th. That is a little bit west from the capital city of Nepal. And another earthquake that happens after 17 days, which is another side. It means east from the capital city. It means the area in between those two heats were affected mostly because of that earthquake. And we Nepal has like 75 number of districts, that is administrative division of Nepal, and like out of 75, then 31 districts were affected, and out of 31, the 14 were most affected and severely affected, and the 17 were less affected. So that is the general scenario. And like we did a post-disaster need assessment immediately after the earthquake, and like which guide us to do the reconstruction work, and like prioritize the reconstruction work, and which area that we need to prioritize, and which area that and how much cost it will require. So everything was given by that PDNA. We call it PDNA. You can find PDNA Nepal everywhere in website, and that could be the another document that might be useful for you as well. So if we look at the impact, that's human impacts, more than 8,790 people were killed, and like over 22,300 people were injured, and more than 8 million people were affected because of that particular earthquake. Similarly, this housing is the is the private housing, where around 500,000 houses were completely collapsed. It means fully damaged houses, and more than 257,000 houses were partially damaged. It means overall more than 750,000 houses were damaged. So that was the scenario. And if you look at the other infrastructure like schools, health, cultural heritage, including your UNESCO World Heritage Site, there are so many damages. So I won't go through the damage of each component, but if you are interested, definitely you can find that in our PDNA report as well. So if you come to the private housing reconstruction scenario, then as I mentioned, there were like more than 750,000 houses were damaged. But during that was the initial data collected during the damage assessment. And during the reconstruction progress was going on, then there are some beneficiaries which were added in the system. It means that maybe because of like they are already separated from the family, and there are so many other reasons as well. So overall, there were more than 836,000 beneficiaries. It means we have to reconstruct all these houses. It means 836,000 houses is quite large numbers. Similarly, there are more than 70,000 houses. Those are retrofitting beneficiaries. And then if you in our scenario, like more than 70% also affected houses are the masonry building, and that is stone masonry. In here in Myanmar, most of the buildings are the RCC buildings, but the scenario could be the same. It means like if I share the what we could to do the reconstruction of houses, then that might be useful for here as well. Then there is a government grant provision for the reconstruction of the private houses, especially for the reconstruction beneficiaries. They get 300,000 Nepalese rupees after the reconstruction, but that work need to be inspected by the engineers, and there were already lots of document, and that reconstruction work need to be like fulfill the National Building Code of Nepal. So there is a provision. So all the reconstruction house were inspected in 3 different stages, and each stages the building should comply the codal provision. So that was the provision, and unless and until the building is not comply with the codal provision, they are not eligible to get the grant money. So for the reconstruction beneficiary, the amount is 300,000 that was distributed in three different stages. In contrast, like for the retrofitting beneficiary, the amount is little bit less, that is 100,000. Why this 100,000? Like we did some retrofitting works before 2015 earthquake as well. We implemented retrofitting in so many schools buildings and very few hospital buildings as well. And our experience says that what we assume in Nepal is like that if the retrofitting cost is around 30% of the reconstruction cost. It means if you are going to retrofit a building and if you are going to reconstruct a building, if the scale of the building typology, everything is same, the cost of the retrofitting will be around 30% of the new building construction cost. So based on that, we have a grant amount, 1/3 of that the reconstruction amount. To do this reconstruction work, then we need a comprehensive and integrated technical support approach, because there is a organizations which established after the earthquake. It is called the National Reconstruction Authority, who has a 5 years mandate to reconstruct all these private houses as well as schools, offices, and all other infrastructure, right? So we need a comprehensive integrated technical approach, and especially for the private housings. And the main goal of these after this earthquake was the multi-hazard resilient reconstruction. So we are not definitely we suffer from the earthquake, but in Nepal there are so many other hazards. There are so many casualties because of the flood every year, because of the landslide every year, and the Nepal is like situated on like from plain region to high mountainous region. So the geographically we are little bit in difficult terrain. So we are facing so many hazards every year. So all the houses should be multi-hazard resilient reconstruction. That is the goal of reconstruction. And there are few approaches that we consider during the reconstruction. Like one is the owner-driven approach, that is especially for the private housing. It means owner-driven means the homeowners is solely responsible to construct his house or her house. It means they are the responsible, just the government will provide the technical supports as well as some financial supports, but the responsibility is of the homeowners. That is the one approach. And actually after the reconstruction of Nepal, this owner-driven approach was like worldwide accepted approach. So another is the build back better. I heard during the technical forum as well, the Myanmar is also following this build back better approach to construct the safer houses. So it means another is the build back better approach. So these are the approach, and for these approaches to achieve the goals that we define, there are some actors, key actors. Always the government is the main actors, because the government has a responsibility to do all this reconstruction work. And another is the house owner, especially for the private housing. Like as I mentioned, that our approach was the owner-driven approach. Then he or she should be responsible and should be aware of these multi-hazard resilient constructions, and they should know about the importance of these multi-hazard resilient constructions. Then along with these, then the very important part is the technical human resource, especially engineer and the masons. It means mobilization of large number of human resource within a very few time is a really difficult job. So but all those peoples need to be well trained, well educated, and they should have some level of experience in the housing reconstruction. So that is the another actors who are really important actors for the reconstruction work. And in our case, the engineers and the masons are the key actors who help us to complete the reconstruction, right? So apart from these, then definitely the community and the private sectors, they are the key actors. They are also the key actors to implement the reconstruction and retrofitting work. So after that earthquake, then we have association like FEDMES, like Nepal Engineers Associations. Immediately after the earthquake, the immediate need was the damage assessment for the public buildings or the government importance buildings that the government has done the damage assessment themselves with the supports from engineering community expertise and other things. But for the private houses, as you saw the data, there were more than 750,000 houses were damaged, and so they need assist from the technical team to having the damage assessment. It is especially the rapid damage assessment to know either their houses are safe to enter or like they are born. Here also I saw some sticker, red sticker, yellow sticker, green sticker, something like that. So NEA deployed more than 3,000 engineers for the damage assessment. After conducting the damage assessment training and they did the damage assessment, and this is absolutely the volunteering work based on the phone call basis. If someone call to the NEA and let's ask for the supports, then NEA provides the technical team to do the damage assessment. That is the very initial phase, but later on also during the reconstruction phase, we have to employ lots of engineers. So NEA has like a large member team, right? So NEA help the government to get engineers, qualified engineers to do the reconstruction work. Along with that, there are so many trainings and like orientations and other professional competencies of engineer communities where the NEA is involving, like from very beginning to till the completion of reconstruction work. So if you talking about the organization structure for the private housing reconstruction, how we work. As I already mentioned that there is a EPIC body, which is National Reconstruction Authority, that is directly under the Office of Prime Minister. That was kept under the Office of Prime Minister to make a quick decisions, and there will be lots of like easy working for them to take some decisions. So that is the NRA, the EPIC body, and under that, I'm just only talking about the private housing. If you are talking about the schools and the health and other monuments, then there are other structure as well under the NRA. But for the private housing, there is a one central level project implementation unit, which we call it a CLPIU, and that was under the NRA, but that is a similar parallel organization with the Ministry of Urban Development. Why? Because in Nepal, the Ministry of Urban Development is responsible to develop the codes, guidelines related to the housing reconstruction. So the CLPIU is under the NRA, but the like officials were recruited from the Ministry of Urban Development. Then under these Ministry of Urban Development, under this CLPIU, which is like in the central level, there are district level project implementation units. Actually, these levels work at the field level. It means we have a 31 affected districts. Then in all districts we have these DLPIUs. It means they will work at the field level. So if you quickly go to the like mandate of each organizations, basically the EPIC body has mandate to do to develop the all required policies. They are basically for the policy makers and resolve the policy making issues on time, and they monitor all the reconstruction work going under the CLPI and DLPI. Then another wing is the CLPIU, as I mentioned, and this is basically the technical wing. Within a CLPIU, there is a private housing, public housing, monuments housing. There are so many wings, but basically the work regarding the private housing is that they are responsible to develop all the technical documents, training to engineers, training to masons, capacity buildings, and basically they are responsible to provide the technical solutions. That is the CLPIU buildings. And they assist DLPIUs to recruit the engineers, and they monitor all the work at the district level. So these are the key works undertaken by the CLPIU. And main importantly, that is the local level unit, which is the DLPIU. DLPIU means they are responsible to mobilize engineers at the field levels. Similarly, masons, social mobilizers at the local level. It means they are responsible to provide technical support to each and every house. It means in our context, engineer were in the every reconstructed houses, not only in a single time, in a multiple times, at least 5 times, but depending upon the requirement. If the demand is high, then they need to go to them to like provide the technical support. So the responsibility of DLPI is to provide technical advice to the house owner and the masons. And similarly, as I already mentioned, that unless and until the building compliance with the codal provisions, then they are not eligible to get a grant. So engineers are responsible to check either the building is compliant with our standard or not. Here I mentioned that the responsible for the inspection. Inspection means there are 3 levels of inspection by the engineers, and they recommend for the grant money. They work at the field level. And after recommendations, the DLPIU provide the tranches of the grant in 3 tranches, right? So this is the overall organizational structure of the housing construction. Then how we started the document, let's say, because we already have a building code in Nepal back in 1994. We have some guidelines, thumb rules, and everything were there. But for the mass reconstructions, it is not possible to implement the building code directly. It means like we don't have enough technical capacity to implement those building codes. So what we did is we develop a standard operating procedure. It means that standard operating procedure made the inspection easy and systematic for the safer construction, right? And those SOP compliance with the National Building Code of Nepal, NNBC, we call it NNBC. And there are actually 4 levels of codes. Category A is the international state of art. Category B is the professional design structures. Category C is the mandatory rule of thumbs. Mandatory rule of thumbs means it is not possible to do the designs of each and every building by the professional engineer, right? So to construct the houses at the village level, so there are some guidelines where the people can use the guidelines. These are the non-engineer building, but guided by the code. It means, so it is called the mandatory rule of thumbs. And 4th one is the guidelines for the rural buildings. These are also the similar type of documents which masons can easily understand, and they can construct house themselves. So initially we developed this SOP where there are the checklist for the engineers with a minimum requirement. It means, as I already mentioned, that the inspection was carried out in 3 stages. The first stage was engineer went to the house owner, and he asked for their requirements. We have a number of designs under this SOP, and based on their requirement, the engineer suggests which design is suitable for them. Either this is RCC or masonry. If the RCC, how many number of stories, and what is the length of the building, what is everything was there. It means that SOP defined everything. This is a very important technical document that we developed based on the National Building Code. And there is checklist. It means during the first stage, engineers go and suggest to the house owner. After the house owner start work, and after the completion of the plinth foundation work, engineer will again go to the field and he will just check. There is a checklist in our standard operating procedures for each building typology. There are several checklists. It's more than 20 number of checklists for different buildings, and he or she just tick either that building is compliant or not. If the building is compliant, then the beneficiary is eligible to get the chance, and he or she will move to the next stage. Otherwise, he or she had to make some corrections, right? Unless and otherwise he or she didn't do that correction, then he or she didn't get the tranches money. So that is this SOP. And this SOP ensure a compliance with the building codes and standard, as I already mentioned, and then it also assists engineers and masons to evaluate, to control the quality, because there is a if you are going to use RCC works, then what will be the ratio of the cement, sand, and aggregate? What will be the ratio of water, and what will be the grade of steel? Everything was mentioned in that particular document. So everything needs to be fulfilled by the engineer and recommended by the engineer. So that type of document is this is. So this is the main document that we develop, and we trained all the engineers before mobilizing on these documents. Not only that, there are so many documents on this document. So another document that we prepare is like, I think this can be useful for FEDMES as well, because FEDMES can develop such kind of documents to assist the government. It means we have a design catalog. Design catalog means general people do not understand to read the like drawing. They cannot understand the drawing, right? So what we did is we provide the model houses with 3D view of the models, with plan, with elevations, and with so many things under within that document, so that we have a large volume of documents and there are several designs, and so that people can select based on their requirement. Let's say there some buildings are 2-room buildings, some buildings are 4-room buildings with 2 stories, some buildings are 3-story with 8 rooms or something like that. There are several designs with several building typology, and people can select in coordination with the technical people. So that is the very important documents, and these documents provide the 3D views of the buildings, so that general people can understand, oh, my house will be like this, right? So that also gives the floor plan, sections, and elevation of the buildings. It means how much story and what will be the area, what will be the dimension. That documents especially gives those things. And the most important things, the structural detailings, usually like which may not be understandable to the general people, but that were illustrated in a such a way that at least the mason can easily understand that documents. And we develop this document in English as well as in Nepali, so that that is easily understandable to engineers as well as masons as well as the house owners. And another thing we provide here is the minimum requirements, what I talked before, right? If you are going to construct the house, then you should fulfill these requirements, and the size of the foundation, size of the columns, number of revars, and the stirrups, how much spacing that you need to provide, everything was there. That is that I call the structural detailing. So that was in the documents. And another thing is, for each type design, let's say if I want to make a 2-story houses with a 4 number of rooms, then what is the manpower required, skill and unskilled manpower required to construct that house? It means the estimation, right? The quantity estimations of the material as well as the human resource estimate, that was also given, so that the government has provided only the 300K. It means that is not sufficient to construct the house, but at least house owner can have some level of understanding that oh, for this house I need this amount of money, and government is providing this amount of money, so I need to manage this amount of money. So that was the approach that we undertaken. And the people were constructing these model houses. I think more than 50% houses they are constructing these model houses. So this is the very important document that we develop. And I think this way we can develop document here in Myanmar as well for the prevailing building. In our case, the masonry is the prevailing one, so that we develop so many designs of masonry buildings and limited design of RCC buildings. In your case, RCC building is the prevailing one, so you can develop so many designs for the RCC, and there might be less designs for the steels and like masonry. So in this way, this can be useful for the beneficiary. So, but what we learned from this document was, we developed this document and we flowed to the all these 31 districts, including how we promote through the televisions and flyers and everything. But what people understand that to become eligible for that grant, we should make these house only, right? But that was the misconception. What we did is, we provided the type designs, but in the minimum requirement, let's say if we provided the room size of 5 meter by 4 meter, then that is not the limitations. There is a limitation. The limit size of the room should be from this range to that range. It means there in the minimum requirement there are so many things, but it is not possible to make a drawing for all those sizes. The people initially misunderstood that they should follow only that design, but later on, after 1 year or something like that, we try to like convince them that they can have a flexibility on that design as well. So that is the one document that we followed. And this one is the really important document, which because of this document we achieve very successful, we have very successful record of reconstructions. Then there is another similar type of document, that is also the design catalog. But why we developed this document is that before 2015 earthquake, we used RCC buildings, steel structures, masonry buildings. Masonry may be of stone or brick or let's say concrete hollow block and other structures. But our code, like because our construction depends on the codes, so we don't have some new or emerging technology, right? Then taking the opportunity of that particular earthquake, we endorse this design catalog volume 2. And this is especially for the you can see the heading of these documents, catalog for alternative construction materials and techniques. It means beyond those conservative materials, we introduce new 17 technologies. In this document, there are 17 number of technologies, new technologies. It consists of light gauge steel structures, any compressed stabilized earth blocks, and so many other design as well. So we produce similar type of. The content is similar design catalog volume 1, but it allows designers to design the buildings with new technology as well. So this is the revolution thing for us after reconstruction. After that, we are using so many new technologies in Nepal. So this is the another document and developed by and approved by the Ministry of Urban Development. So we develop few documents and we have minimum requirements and SOP. But after having a couple of years of reconstructions, then we found so many non-compliance building, right? Non-compliance means building were constructed there, but those buildings were not comply with the minimum requirement that we provided to them. And unless and until that is not complied, we are not giving them the grant. It means what happen if something is found non-compliant? Then what we actually we found so many non-compliance issues, and that was reported from district level, local level to the central level. That the engineers they don't have a solution, right? Because each and every engineers are not experienced enough to provide solutions. So they are taught to comply the SOP, but they are not taught to do the designs for the non-compliant issue. Then what we did is we developed one correction and exception manual. It means if the buildings which are under constructions contains, let's say 90% of the features, the building has 80-90% of the features, but the building misses few features. Then what should we provide the correction exception manuals, and we train engineers, and these manuals gives the what could be the exception while constructing the buildings. There might be some let's say some bar. If there is a 8 number of bars, only the 6 number of bars are provided. If there is some band, we have to provide the band is missing. Then we give the number of exception cases in the document, and along with that exception cases, we provide the common defects. What are the common defects, possible defects, based on our field experience as well as based on our assumptions, engineering analysis. Then we provide the corrections for each and every solutions. It means this document also help us to increase the compliance rate from, let's say, 60% to 100%. It means this is a very important document that we develop after a couple of years to make the building compliance in the field. And after having the compliance, after having the correction measures in the field, in the real field, only after that we again went to the inspection of the buildings, and then we recommend for the another grant money. So this is another very important document that we followed. And definitely, if you are going for the mass reconstruction, then you will definitely face non-compliance issue, and you have to do the corrections, because we are talking about the multi-hull resilient buildings. We are not talking only about to give the grant money. We are thinking about for the future other aspect, right? So this type of document, definitely here also we have to make this type of documents, so that if there
Excuse me, engineer Bipin, can you wind down your presentation now?
Okay. So these are documents, and after that we have other we have some retrofitting documents as well. So we already have so many retrofitting design guidelines, based on these, we developed manuals so that people can execute the retrofitting works in the field. It means we have a field guidelines manuals so that there is a steps like implementation steps and with different solutions to do the retrofitting of the building. So this is the another important document that we implement, and these documents were basically focused on those 78,000 houses. So these are the documents that we developed, and these documents basically gives us the vulnerability of the buildings and what could be the possible solution to make the retrofitting. And we gave the number of alternative solutions so that these engineers, masons, and the house owners can select the best options among different options. So, so then how we manage the technical human resources in the field? This is also another important things. Then what we did is at least under the district level, there are few municipalities, and within the municipality, there are few wards. So we provided at least one engineer or sub-engineer to the ward level so that he or she will be able to visit all the house owners and provide the technical support. That is the one that we that were like sent to the field, and there were the technical experts, structural engineering experts at the district level who can provide the if there is some problem at the field, every engineer cannot solve those issues. So structural engineer provide the solution at the field. That is provided at the DLPI district level units, and there is a other unit in the central level. If the problem is still unsolvable the district level, then there is a task force at the central level, and I was reading that task force, and like we provide the solution at the central level, from the central level in coordination with the different professional societies and like experts and like academicians. So this was our like technical human resource management, and the theme was we should not left any problem unsolved. We have to solve the technical issues as soon as possible to benefit the beneficiaries, right? So what we did was more than 3,000 engineers were deployed at once at the field levels. Similarly, we deployed 246 number of social mobilizer at the later stage, so that they help us to like motivate the beneficiaries for the reconstruction or retrofitting works. We mobilized more than 755 mobile masons in the highly earthquake affected area, and 30 number of structural engineering experts at the district level, not at the central level, at the district levels, and there are 8 number of monitoring evaluation experts who are going to like monitor all those things at the field level. So if you are talking about the capacity buildings, then there were detailed damage assessment trainings, which was done by the NEA as well as the government, and there were the we can say there were lots of training for the all technical things that required for the reconstruction, from inspection of the buildings to the like building codes, and then training on the construction of infrastructures, on the job training to mason. It means the real model will be constructed at the field, and the engineers and masons will be trained on the field. So that kind of approach we'll consider during the capacity building activities. And I'll share these slides to you so that you can see the other features here. So based on those initiatives, then if you look at the data, then more than 90% buildings were reconstructed, and this is one of the successful story. And but in terms of the retrofitting, there are less than 6%. So we don't have a good experience in the retrofitting. So you can see the data here, the status of reconstruction work. Then I'll quickly go to the challenges. What are the challenges that we faced for these reconstruction work? Like the first one is the it took almost a year to set up the NRA, which I call. So that was the most important challenge that we faced during the initial phase. Then another is the lack of trained human resource and to do the reconstruction work. So we have to train all the people after having the disaster. Then another thing is the difficult geographical terrain. It means our country has like almost 100-meter level to the 8,800-meter level. So that is a really difficult terrain, lack of transportations and accessibility. So that is another challenge that we face. And very important thing is the digitization data. It means initially we don't have the proper digitization of data, but there is a mandatory that to give the grant to the beneficiary, we have to digitize all the reconstruction data into the system. So that was the another challenge we faced. And later on, we digitized all more than 800,000 building houses data. So we have that digital information of those data. That was the initial challenges. And as you saw from the data, retrofitting was the challenges. Similarly, the urban recovery, because of the large amount of money is required and the large number of houses were there. So urban recovery was the most difficult part. So if you compare with the rural housing recovery. And similarly, there are a couple of things that I want to call here, that we developed some resettlement. You can see the first photograph. Actually, that was nearby our epicenter, and we constructed you can see there are more than 600 housing at a place. It means we have done so many resettlements, right? If the area is vulnerable, then we shifted those people from those vulnerable area to the another place. And there are very successful story of this resettlement, but there are few resettlement where we have a bad experience because of because there is a lack of access to the land family. Their old house was and farming area was in the another inn, and they came to the another place, so that there is difficulty of doing their traditional economic activity. So that is the one lesson learned from the important lesson learned from this integrated settlement. And another lesson learned was the people constructed their houses only to receive a tranche. It means they are still living in a vulnerable houses, but they make a 1-room or 2-room houses to receive a tranche. That was the another challenges that we faced during the reconstruction, among different challenges. Then at the end, I come with the key learnings that might be useful for the reconstruction of Myanmar as well. So one thing is the resilient construction techniques were adopted and internalized by the local community. At least after the earthquake, people understand what is the earthquake resilient constructions, what is the disaster resilient construction, that they know from our initiatives, which is the big achievement actually. These days, at least people, when constructing the building, people are talking about the resilience thing. So that is the one very important learnings from our experience. And a robust enforcement mechanism with trained human resource. More than 5,000 engineers were trained, and more than 80,000 machines were training. So that is a very good achievement in terms of capacity buildings. So as I already mentioned, building back through the owner-driven approach, that was one of the successful story from our sides. And one thing is the socio-technical assistance for the vulnerable people, the people who are from the left behind society, and the people who are from the vulnerable people. It means especially able peoples. They were assisted through social technical assistance. They were prioritized in the reconstruction work, and that is also the one of the good example for our reconstructions. So that we make a making home accessible to all. It means we make a home to the disabled people or especially able people. That is another achievement that we done. And another thing was all the reconstruction.
Engineer Bipin, can you conclude
Yeah,
very soon now, right, within the
sure,
minute?
sure,
Yeah.
sure. And all the data were and system and MIS were played a vital role in the reconstructions. And there were 299 vulnerable settlements were made there. If the region is really vulnerable, then we shifted them to the good places, so safe places. So that was another achievements. And we did we standardized so many guidelines and designs, including the seismic design course. So that is another achievements. And at the end, for the future resilience, we established the one permanent structure that is called the National Disaster Risk Reduction and Management Authority, where all the knowledge will transfer to that department. So these are the key learnings that we achieved from our reconstruction. I think this much for today. If you have any questions, then I will definitely try to answer it. And you can
Engineer, yeah.
Thank you very much.
Engineer Bipin, I think we are run out of time, so sorry, there's no time for questions. But FedMES is actually going to do a short agenda now. We are almost done, but not quite. So, Mr. Somin, can you please take over and do the remaining part of the agenda?
Thanks.
Sorry, Dr. Udai. Can I ask only one question to Mr. Bipin? Hello, can you hear me, Dr. Udai?
Yes.
Yeah, sorry, can I ask one question to Mr. Bipin?
Okay, maybe really quickly. Yes.
Yeah, only one.
Carry
Yeah.
on, carry on.
So actually, I'm very interested about the design catalog for reconstruction of earthquake-resistant houses. So it means that your Nepal housing reconstruction program, which belongs to the government or maybe your organization only?
No, actually, this belongs to the government, and that design were developed by the Ministry of Urban Development in coordination with all the stakeholders.
Okay, understand. So it means that in this catalog, they already put all the design, like maybe this size, that size. and
Exactly.
It depends on the span of the building, something like this. Okay. So if, as long as the people, they follow this kind of building, they don't need to submit the calculation report to the government, isn't it?
Exactly. That's why we developed this document, because it is not possible to design each and every building by the house owner, right? To make them easy work, we provide them the, let's say, if you are going to make a 1-story buildings, you can make from 3 meter to 5 meter size with this much room size and this much building size. Everything was given in that particular catalog, so that they can select among the different designs and they can construct the house.
This is really good and
Yeah.
very easy and
Exactly.
save the time.
Yeah.
So sorry, one more thing only. I found out robust enforcement mechanism with trained human resources. So around 5,000 engineers and more than 80,000 masons were trained. So were they trained by your organization or?
Actually, what we presented is everything was done by the Nepal government. They may took like assistance from the engineer associations, from the different partner organizations, donors. But there is a one door policy. One door policy. So if someone wants to like do some intervention there, they should come from the government. So that was the policy. So all these things was done by the government actually. Thank
So much. Your government, I think to your government.
Yes,
Thank you.
Thank you very much.
Thank you. Thank you. Mr. Somyant, please go ahead. So I believe this is for appreciation of engineer Bipin Gautam, who participated in the technical forum the last 2 days and today in this seminar, in this session. Thank you very much. Thank you.
With ACECC logo.
One other thing, announcement. We will have a session 3, third session, and it'll be on 3rd of September, same time, same place, and we will make an announcement in detail a little bit later. And there'll be 4 more new exciting speakers from different countries.
Section 3,
so
September.
3rd of September, same time, same place, and we will we already have speakers lined up, and I'll be working with FedMES to give all the details, and we'll have a flyer on that also circulated soon. So thank you very much for especially the speakers and all the attendees, and thank you very much to Myanmar Engineering Society. I really appreciate your help and coordination on this. So again, it's been very exciting, and really appreciate everybody's contribution here. Thank you very much again.
Thank you very much, Mr. Udai.
Thank you.
Thank you so much, Dr. Udai, ACECC members and speakers. Thanks a lot.
You're welcome. Thank you.